We are running out of physical room to build better computers. As components shrink down to the atomic scale, the traditional method of pushing electrical charge through a wire is hitting a strict physical limit. To keep scaling, engineers are turning to spintronics. Instead of only relying on an electron's charge to carry information, this method utilizes a quantum property called spin, treating the electron like a tiny spinning top. Tapping into this property allows for data processing that operates at higher speeds while requiring a fraction of the energy used to move bulk electrical charges. This shift to spin-based computing represents a necessary departure from traditional charge flow logic, providing a viable path forward as we reach the limits of silicon. To control these spinning electrons, engineers rely on magnetic materials, typically standard ferromagnets. But there is a major problem. When you cram billions of tiny ferromagnets onto a nanoscale chip, their internal magnetic fields leak outward. These stray fields crash into neighboring components and corrupt the stored data. One alternative is the antiferromagnet. These materials have perfectly opposed magnetic sublattices, meaning their net magnetic field cancels out. They operate in absolute silence, causing no interference with their neighbors. However, that silence comes with a penalty. Antiferromagnets lack the internal magnetic asymmetry required to actually inject or read an electron spin. Without that asymmetry, the data signal fails to register. This leaves spintronics in a trap. Traditional magnets are too loud, and perfectly compensated non-magnets are too quiet. The industry needs a middle ground, a material with a very low magnetic moment. To find that middle ground, physicists look to half-Heusler alloys. These are highly customizable, crystalline structures where researchers can mix and match metallic elements to tune their exact properties. As detailed in this research paper, a team recently synthesized a first-of-its-kind half-Heusler alloy made of cobalt, vanadium, and germanium, known as CoVGe, specifically searching for that low magnetic moment. Before creating it in the lab, they consulted a physical law called the Slater-Pauling rule. CoVGe has exactly 18 valence electrons. According to the rule, this specific atomic balance dictates that all magnetic forces should perfectly cancel out. Because of this 18-electron structure, the math predicted that CoVGe would act as a semiconductor with exactly zero net magnetic field. Every calculation confirmed the same outcome. On paper, the behavior of CoVGe was entirely predictable. Then the team built it. They used an arc melting technique, subjecting the raw elements to superheated energy to fuse the physical sample. But when they tested a new material, it broke the rules. This graph shows the temperature-dependent electrical resistivity of the sample. Instead of acting like a semiconductor, the resistivity goes up with temperature, proving the material behaves like a metal. It wasn't magnetically dead either. Looking at this second plot, specifically the S-shaped narrow hysteresis curve at 5 Kelvin in the top right, we see the clear signature of weak itinerant ferromagnetism. Further tests revealed a tiny yet measurable saturation magnetic moment of 0.13 Bohr magnetons, alongside an unconventional linear positive magnetoresistance at low temperatures. The lab-grown alloy completely defied the Slater-Pauling rule. Physicists were left with a metallic, slightly magnetic mystery that contradicted their initial models. To find the source of the discrepancy, researchers used first-principles calculations to reverse engineer the atomic structure. They discovered a microscopic flaw known as Antisite Disorder. During the intense heat of synthesis, atoms occasionally take the wrong seat in the crystal lattice. This chart visualizes that error rate. The red curve on the left tracks what happens when you introduce swapping disorder between the cobalt and vanadium atoms. The calculations found that about 10% of these atoms had traded places. This 10% swap directly populates the Fermi level. As seen in the density of states graph on the right, those extra states at the zero energy line provide the physical reason for the metallic conductivity and the unexpected magnetic field. The anomaly was not a failure in the synthesis. It is a natural, hidden quirk embedded directly in the material's atomic architecture. This specific microscopic imperfection is the bridge spintronic engineers have been searching for. Because of the Antisite Disorder, CoVGe possesses just enough magnetic asymmetry to successfully inject and detect an electron's spin state. Yet, because its total magnetic moment is restricted to a faint 0.13 Bohr magnetons, it remains quiet. It manages data without leaking the stray fields that would disrupt nearby components. CoVGe hits the sweet spot between loud ferromagnets and completely silent antiferromagnets, providing a platform for high-density spin-dependent transport. By leveraging these atomic scale imperfections, researchers can now bypass the physical limits that have long restricted traditional semiconductor materials. Removing the stray field barrier allows for tighter component packing, enabling devices to increase in processing power even as they continue to shrink. Final takeaway: CoVGe proves that the future of high-density logic doesn't require perfect crystals. Instead, it requires the precise ability to tune these magnetic sweet spots at the scale of a single atom.